Hello, ladies and gentlemen. My name is Beniha Youssef. I'm a PhD student at High National School of Electricity and Mechanics, University Hassan II of Casablanca, from Morocco. I'm working on the anaerobic digestion process optimization using AI algorithms. So today, I'm gonna present my work entitled of optimizing total ammonia nitrogen monitoring in various anaerobic digestion systems, a machine learning approach with XGBoost and AdaBoost algorithms. This work was supervised by Professor Sadiq Mohammed and Professor Fair Abdurrahim. Let's move now to the content. Firstly, I'm gonna begin with the introduction, in which I will give an intuition about the anaerobic digestion process and why the prediction of the concentration of total ammonia nitrogen is crucial. Secondly, I will explain the methodology which we follow to realize our target. Thirdly, it's the section of the results and discussion, in which I will mention the results obtained by the models, and I will give a comparison study with other results in the literature review, followed by future importance based on main shape values analysis, and finally I will set some models limitations and future exploration. Let's move now to the introduction. Anaerobic digestion is a process in which microorganisms degrade organic matter without utilizing oxygen and produce biogas, which could be upgraded as electricity or heat. And the residue digested could be applied in agricultural applications as biofertilizer. So, what are the phases of the process of the anaerobic digestion? As we can see in the figure in the left, the process begins with the hydrolysis, in which soluble organic molecules produced, and the second phase is the acidogenesis, in which volatile fatty acids could be generated, and the third phase is the acetogenesis, in which acetic acid and dihydrogen and carbon dioxide could be generated. The final phase is the methanogenesis, in which biogas could be produced in two ways. The first one is the direct degradation of acetic acids, and the second one is the utilization of dihydrogen and carbon dioxide. So, an excessive formation of total ammonia, which is a byproduct of proteins, could rise the pH of the process and subsequently lead to the process inhibition. And on the other hand, a lower production of ammonia conduct to a minimum food for the bacteria, therefore the process inhibition. After that, a low production of biogas. So, it is significant to monitor or predict the total ammonia nitrogen concentration for maintaining the process stability. For this reason, different machine learning models were suggested on the literature review. And in our study, we suggested two models, XGBoost and AdaBoost, which could be considered as soft sensors. Let's move now to the methodology. So the methodology which were followed in this study was divided into three parts. The first one is the data collection and pre-processing. So the data composed of more than 2000 units of input and output were collected and prepared by considering six input features and one output, which is the TEN. The data was splattered into three sections: the 70% for training, 15% for cross-validation, and 15% for test. After that, we applied the data scaling using standard scaling. The second part is the model development and construction, in which the train and cross-validation data were fed into the models, in which we apply a nested loop considering three tuning parameters for the two models. Number of estimators ranging from 50 to 1000, rising by 15 in each step for XGBoost, and ranging from 50 to 500, rising by 15 for AdaBoost. And for the maximum depth and the learner rate, we considered the same intervals for the two models. In each step, a model was created, and the root mean square error and R squared as accuracy were calculated based on cross-validation dataset. After that, we selected the appropriate model based on these metrics. And the final part of the methodology is the models evaluation, in which we applied the selected models to the test data and we evaluated by using the same metrics. Moving now to the results and discussion part. And we will begin with the XGBoost. As we see in the figure in the left, this figure presents the obtained RMSO and R squared for each XGBoost model created inside the loop, considering maximum depth as a parameter. As we can see, the minimum root mean square error with the maximum R squared corresponds to the maximum depth, equal 4. After that, we fixed this parameter and we obtained the figure in the right considering number of estimator as a parameter. Sorry. The minimum root mean square error with the maximum R squared correspond to number of estimators equals 700. After we fix the previous parameters, so for the maximum depth, we fixed this number at 4 and we fixed the number of estimators at 700. This figure also illustrates the appropriate linear rate, which is 0.01. So the selected XGBoost model is the model with maximum depth equal 4, number of estimators equal 700, and linear rate equal 0.01. Moving now to the AdaBoost. For AdaBoost model, the same methodology was applied. The figure in the left presents the obtained root mean square error and S square for each AdaBoost model created inside the loop, considering maximum depth as a parameter. As we can see, the minimum root mean square error with the maximum S squared corresponds to the maximum depth equal 5. After we fixed this parameter and we obtained the figure in the right considering number of estimators as a parameter. The minimum RMSO with the maximum S squared corresponds to the number of estimators equal to 100. After that, we fixed the previous parameters and we obtained this figure which illustrates that the appropriate linear rate equal 0.01. So the selected AdaBoost model is the model with the maximum depth equal 5 and the number of estimators equal to 100, linear rate equal 0.01. And we take decision tree as the base estimator. Moving now to the models comparison section. After defining the optimized models, we applied them to predict the total ammonia nitrogen concentration, and the accuracy obtained was summarized in this table. The test data results confirmed the cross-validation finding, with the two proposed models achieving considerable R squared, with XGBoost had the highest one with the value of 0.94 and the minimum root mean square error equal 0.22, compared to AdaBoost, which showed good accuracy of 91% and an error of 0.3, which is higher compared to the error obtained by XGBoost. We can observe that the optimized XGBoost and AdaBoost models in this study exceeded the previous results by 5% and 2% respectively in terms of accuracy if we considered SVM as a reference, and by 7% and 4% if we considered EEN or artificial neural network as a reference, indicating that hyperparameter tuning improved models' performance and demonstrates the potential of XGBoost and AdaBoost as robust alternatives to SVM and EEN for forecasting TEN in various anaerobic digestion systems and considering them as soft sensors. So these figures illustrate the prediction results of the selected models versus the experimental values of TEN concentration. The XGBoost model consistently aligns forecasted and actual values across most sample index intervals, with only slight deviations in middle and high concentration TEN values. This demonstrates its efficient recognition of nonlinear patterns and interactions due to its gradient boosting architecture and regularization techniques. The AdaBoost model shows more extreme fluctuation, suggesting potential data noise or outliers. Moving now to the feature importance analysis. Using the main shape values. The shape research showed differences in how XGBoost and AdaBoost interpret techniques for total ammonia nitrogen. XGBoost highlighted organic Lloyd rate as important for predicting complex substrate microbiome interactions, while AdaBoost focused on temperature simplifying ammonia inhibition. Both models noted the pH's minor role and showed low relevance for volatile fatty acids. This suggests the need for plant-specific models with XGBoost for accuracy in diverse conditions and AdaBoost for temperature-focused analysis. So, we observed that the two models showed good accuracy and potential for predicting total ammonia nitrogen concentration. But there are some limitations that we should see it in this presentation and some suggested perspectives and the future exploration which we are working on. So, the XGBoost model and AdaBoost model are sensitive to noisy or incomplete data. So, it's significant to expand datasets to include diverse substrates, reactor types, and operational disturbances to improve model robustness. And also, the dependence on past data restricts the adaptability to new substrate or process variation. So, we suggest that to train models on a broader variety of input conditions and integrate transfer learning to improve adaptability. Also, the AdaBoost failed to capture organic Lloyd rate dynamics, which is in the shape value equal 0.007, highlighting its weakness in dynamic environments. So, the use of hybrid models like AdaBoost plus LSTM or TCN to capture time varying behavior more effectively. And also, the shape values provide static future importance and miss time-dependent interaction crucial for real-time control. So the development of the dynamic shape or time-aware explainability tools for monitoring evolving process behavior. Thank you for your attention, and if you have any question, I'll be glad to answer. Thank you.